Okay, so welcome again to our course, Artificial Intelligence. This is the first lecture where we should put us on a common ground of what we expect you to already know and where we will be heading, actually. And we will talk about the first topic about decision tasks. This artificial intelligence course actually follows the bachelor course, Cybernetics and Artificial Intelligence, and it somehow builds on it and expands the knowledge from that course. So it may happen that some of the topics that we will talk about, you may have heard about them also in the Cybernetics and Artificial Intelligence course in the bachelor course. Excuse me. And the decision tasks are actually one of those topics. I think most of you should have already heard about it. Just a quick survey among you. How many of you have passed or have gone through the Cybernetics and Artificial Intelligence course? Answer yes if you had it, and answer no if you did not go through it. So the results seem to be somewhat expectable. Most of you have passed that course, and there are some 7, maybe up to 10 people who did not pass it. Okay, thank you. Oh, now I understand. So if I put the survey like Anone, with the possible answers Anone, so our foreign students may not understand really. So I will have to be careful with that, okay. Great. So let's first start talking about what an artificial intelligence is for each of us. What is our impression or belief of what artificial intelligence should be. And then we will define how we will understand the artificial intelligence in this course. And then we will move to the decision tasks. And I will switch off my camera because I want to save some bandwidth just in case. Yeah. So artificial intelligence. In a broad sense, artificial intelligence studies a lot of things, and a lot of scientific areas have some kind of overlap with artificial intelligence. And that's because it encompasses the whole process of, let's say, perception, understanding, reasoning, prediction, and acting in a real world. And this process is done by some artificial entity that we can call either agent or robot. Very often these two terms are used quite interchangeably. They are synonyms, but in some more restricted sense, the agent usually means something like the software part, which is responsible for the intelligence, while the robot may mean the hardware part, the device that actually acts in the real world. But in a sense, artificial intelligence is by many people perceived as the science to create an intelligent entity that either imitates or improves the human behavior and its effects in the outer world, or that imitates or improves the inner human mind processes and reasoning. So there is this distinction between just imitating or improving the actions of a human being, or modeling the human mind processes in the brain. So I have the first question for you. What is AI for you personally? So you can answer A, B, C, or D, whether in your opinion the primary goal of artificial intelligence is to build machines that either think like people, or B, act like people, or C, think reasonably or rationally, or D, act reasonably or rationally. So please tell me your opinion. What do you think? What is the right view, but your personal view of AI? Okay, so I have the majority of answers. Thank you. So it's like the answers are somehow ordered from the least popular to the most popular. Let's talk about these possibilities on the following slides. All of these options that you had were at some point in time part of artificial intelligence, or have a close relation to artificial intelligence. And some people, some researchers actually take one of these four options as their personal definition of artificial intelligence, right? So no matter what you chose, it can be that way for somebody, even for you. But I would like to define what an artificial intelligence will be for us in this course. So the first option, to make machines think like people, nowadays probably is not considered part of AI anymore. It is a kind of mix of cognitive science and computational neuroscience. So it is more like modeling the human reasoning processes as they happen in the brain, which means that you have to really model the brain mechanics, and we do not do that in artificial intelligence much. The other option was that AI is to make artificial machines act like people. So this is a plausible option, fine. The question is whether you really want to mimic even the mistakes that the humans do. This is basically the option that Alan Turing popularized in his Turing test, right? If you conversate with someone and you are not able to say whether it is a machine or whether, if you are not able to discern whether it is a machine or a human, then probably the machine is intelligent, right? That's the Turing test. But an important think in human behavior are actually mistakes and not really rational decisions made all the time. We are influenced by feelings and other external factors. And the question is whether the machines should be influenced like this in the same way. But I think that modeling these mistakes is actually a big part of not being discernible from a man, right? Because if the answers are too perfect without any mistake, without error, then you may start thinking, hey, this is too perfect, right, for a human. So this may be a very good machine. Okay, the third option, machines that think rationally, this is some kind of strong AI, meaning that it requires some correct thought process. This is on the boundary of philosophy and logic, and yeah, you should be able to prove that your thought process is optimal without mistakes, etc. And this is still somewhat more distant to what we will consider AI in this course. So we will try to build machines that act rationally, that behave rationally, reasonably, optimally. And during the whole course, we will basically see something like this. The last sentence, we will try to maximize the expected utility of the outcomes of our decisions or actions. Or in other words, we will try to minimize the expected penalty of the outcomes of our decisions. Now, the good decisions will be based actually on some cornerstones, if you want, on some foundations. And one of the foundations may be that you would like to account for similar situations that happened to you or to the machine already in the past, right? So to learn from historical data. And this is something that machine learning basically solves. You have some data set on which you can learn, and you will apply the learned knowledge for future data. The other thing that could help you make good decisions is actually modeling the world. Create a good model of the world. And using this model, you can either run some simulations to see what the consequences of your actions, of your decisions are in the real world, or you can use it in planning. So model of the world is very often a substantial part of inference or planning, and we will see several of them in this course as well. Okay. Yeah, these are not, this is not complete list of scientific disciplines which are important for AI, which have quite a lot of overlap of AI or that belong to AI. You can see here something like knowledge representation. You must be able to represent the knowledge, either the learned knowledge or a model of the world in a computer. You must be able to reason about that knowledge or with that knowledge. You must be able to plan your action. And if it comes to, some inputs that comes to the machine, you must be able to recognize some patterns that you have already seen in the past, for example. and learn from the available data. Of course, multi-agent systems belong here too, because many people don't actually, or very often we do not build a single machine to solve your task, but we will probably use multiple intelligent machines to cooperate and coordinate themselves when solving certain task, and this is what the multi-agent systems study. Yeah, and this is on the right hand side, this is the input output of your artificial being, right? So either you can give it inputs in the form of natural language, which may be one way how to communicate with the artificial entity, and then you must study the natural language processing somehow. Maybe the entity has a kind of camera or lidar or something like that, and you are in the field of computer vision, how to make sense out of images or videos taken by that robot. And of course, you need to somehow, very often, the agent or robot moves in the real world and somehow affects the real world. So you must study how to move, how to estimate where you are, how to navigate, how to take something in your hand when you are a robot, how to release it correctly on the right place, etc. So this is all what the robotics basically solves. And we get to the course outline. Today we will talk about the Bayesian and non-Bayesian decision tasks. And then we will start quite large block of machine learning. So this is all about machine learning, various methods. Then we will have a block of probabilistic modeling with the help of hidden Markov models, mostly Bayesian networks and hidden Markov models. And then we will have 3, let's say, separate lectures on constraint satisfaction problems, planning, and scheduling. And yeah, so that's what you will see this semester in this course. So are there any questions regarding this introduction to the course? So I don't see any, so let's go further. Okay, decision tasks and decision making. Okay. This is something that you have already met in the course Cybernetics and Artificial Intelligence. I will repeat most of it here because some of you did not actually had that course, and it will be useful for us when we later will talk about hidden Markov models, because in a way hidden Markov models are a sequential extension of this Bayesian framework for decision making. Okay, so the goal of decision making is, of course, to make decisions. So in a certain task, you may have some kind of object or subpart of the real world, and you would like to make decisions based on your observations of this subpart, of this object. And the object or situation of interest may have some part which is observable, and we will denote it usually by X, and we will call it an observation, sometimes even evidence or measurement or feature vector, etc. And an object will also have some kind of hidden, unobservable state, which is unknown to us, but which exists. Yeah. And for certain observation, X, and unknown but present hidden state K, we would like to make a decision or choose a decision from the set of possible decisions. So for example, you can have, I have two examples here. If you would like to use radar as the detector of an aircraft, then what the operators of radar usually see is some kind of reflection on the screen. And the reflection may or may not be from an aircraft. It may be something else than aircraft. So the observation X is some description of the reflection that they see on their screens, and the hidden state, the unknown, is whether it really belongs to an aircraft or not. And our decision in this task would be to estimate or guess or predict the true hidden state, meaning to predict whether it is really an aircraft or not. Another example may be from the medical sphere. Patient diagnostics, for example. An observation X would be a set of all the diagnostics measurements that you can do on a patient, right? What is the body temperature? What is the blood pressure? How the patient feels? Whatever, right? But these are your observations. And your hidden state, unknown, may be whether the patient suffers from some kind of disease, possibly from what kind of disease. And that's what we want to estimate. Or the decision, the set of decisions may be even different from estimating the hidden states. Maybe we would like to choose the suitable treatment that is suitable for the hidden state, which we do not know. It is important to note that the observation is almost always noisy, incomplete, somehow corrupted, or may contain other forms of uncertainty. So we have to deal with the uncertainty somehow, and we will use a probability theory and statistics to deal with uncertainty. So any questions to this definitions of observations and states? So it seems that everything is clear. Okay, so given the observations, the set of observations, the set of hidden states, and the set of decisions, the goal of the decision strategy design, if you want to design a decision strategy, then you probably, well, not probably, but you want to create some kind of decision function queue that maps the observations to decisions. So you make an observation and you assign one decision for each possible observation. That's the decision strategy. And of course, you would like this decision strategy to be somehow good, to be even maybe optimal from some point of view. So we would like to create a decision strategy which is optimal with respect to certain criterion, and we will see that criterion later. And you will have to take into account the uncertainty of the observation. Probably the hidden state somehow influences the observation, right? So some information from the hidden states transfers to the observation that you can see, and based on this information you are about to choose the right decision. The problem is that for example, different hidden states may express in very similar observations, such that based on the observation itself you will not be able to discern between the hidden states, etc. So there is many possible issues that you can actually run into. So this is the general goal of the decision strategy design, to design decision strategy optimal with respect to certain criterion. If we start talking about Bayesian decision theory, then we will have to say that the Bayesian framework for decision strategy design requires the complete statistical information about the object of interest, meaning that you need to know this joint probability distribution of observations and the hidden states. And also, the other requirement is that you need to have some kind of suitable penalty or utility function that tells you how good a decision D in a situation K, in a hidden state K, actually is. So for each pair of hidden state and decision, you will get a real number that will tell you basically the utility, the money you earn, or the penalty, the money you lose, when you make the decision in hidden state K. And then there is a very broad class of decision making that is actually non-Bayesian, that deals with cases when one of these two things, or maybe both of them, is actually missing. When you do not have the complete statistical information in the form of the joint probability distribution, or when you do not have access to a suitable penalty function. So this is the definition of concepts for, let's say, Bayesian decision theory. We already know what an observation and a hidden state is. Then there is this joint probability distribution that is required for the Bayesian framework. And this is just a function from the product of observations and hidden states to some real value from 0 to 1. It's a probability distribution. Very often it may be given in a factorized form, right? Like the probability, the prior probability of the hidden states and the conditional probability of observations given the hidden states. So this is very often more suitable form of specifying this joint probability distribution. And you would like to design the decision strategy, which is a function from the observations to the decisions. And you need the penalty function to actually decide which of the possible decision strategies is actually the best one, which is which has the lowest, let's say, penalty on average, right? And then there is this risk, which is actually the average penalty or the expected penalty you would expect from using the strategy Q. So each decision strategy, each function that maps observations to decisions has an associated risk. And this is the criterion that is used to evaluate the decision strategy in Bayesian tasks, and it is defined as the mathematical expectation of the penalty when using strategy Q. And if I'm not mistaken, I have a question for you on the next slide. Yep. So think about it. We have a decision strategy that is this function from the set of observations to the set of decisions, right? It is a mapping. And we will consider this example that we have a coin which may be biased, which means that the heads and tails are not 50-50 distributed for this coin, right? And to somehow evaluate whether the coin is biased or not, you will observe 5 coin tosses. So you will count how many of the 5 tosses you will get, how many times you will get heads. And that's your observation. So observation is a single number from 0 to 5, which tells you in 5 experiments, I have observed 0, 1, 2, 4, 3, 5 heads. And based on these observations, you are about to decide whether the whether the coin is fair, or whether it is biased, meaning unfair, or whether you don't know, such that you don't have enough data to decide, for example. And my question for you is, how many different decision strategies are possible? How many functions that map observations to decisions are possible? And here you have 4 possible options to choose from. And let me know what you think. So A, B, C, D. You have 2 hidden states, 6 observations, and 3 possible decisions. Okay, when I ask how many different decision strategies, I mean all possible ones, not only the reasonable ones, but really how many possible structurally correct decision strategies are there.
May I ask if there is 5 or 6 tosses? In the text there is 5, and in the observation number of head is from 0 to 5, so it counts to 6.
That's correct. In
So
5
6.
tosses, you may observe 0 to 5 heads, right? The head can come up never in those 5 tosses or all the time.
Okay.
So that's why there is 0 to 5. Okay, so the answers actually stopped coming, or their number does not increase. So let's stop the survey. And it seems that the answers are quite distributed, but still the winner is the option C, right? Seems that 16 of you actually think that it's this 729. So what's the correct answer here? Okay, so you have actually 5 possible observations, right? 0, 1, 2, 3, not 5, 6, 3, 4, 5. And for each of this observation, you may decide, for example, maybe one strategy would be to say that the coin is fair no matter what happens. This is one possible decision strategy. Another possible strategy would be to think that the coin is fair in all cases, maybe but the last one. Maybe you will say here it is biased. Another decision strategy would be to think that the coin is fair, but I don't know. I don't know how to write it. Okay. So these are 3 possible decisions for the 5th observation, for the 6th observation, sorry. And there are 3 possible strategies, but you may have any combination of these 3 decisions on these 6 places, right? So you have 3 possibilities here, 3 possibilities here, 3 possibilities here, 3 possibilities here. So it's really 3 to the power of 6 possible strategies. Of course, many of them are completely unreasonable, because you would expect that a fair coin would give you maybe 2, 3, right? 2 heads, 3 tails, or vice versa. Maybe if you had a very biased coin, you would say, okay, here and here I would have biased coins, and maybe in between I wouldn't be able to decide, which is also a decision, right? The decision not to decide. So yeah, reasonable strategies would somehow be made of higher probability of biased coins here and here, and higher probability of unbiased decisions here. But all of these that I have just listed are possible decision strategies. And yeah, there is 729 of them, even in this very, very small example. So the number of decision strategies that you can design grows exponentially quickly with the number of observations, number of observations that you can make. And that's the issue, right? Because you can, for example, evaluate them all like a brute force approach. But if you want to do it more intelligently, more efficiently, then how to do that? So thank you for your answers to this example. This is again some kind of list of applications such that you realize that the observations and decisions may be quite diverse beasts or types of entities. So it may be some kind of vector of real values, which is quite often the case. And decisions may be a value of the coin, for example. But the observations may be also some gene expression profiles, right? Or it may be an image, or it may be a signal or process depending on time, right? And again, the decisions may be very simple, ranging from a simple yes, no, true, false, or something like that, to something quite complex, like choosing the right diagnosis from the possible set of diagnoses. In speech recognition, the decisions are actually words. So if you hear a signal, a sound, you must somehow turn it into a word, into the meaning of the sound, right? Etc. So there are many, many different examples and many types of observations, many types of decisions that you can make. Okay, this is just a side note. Here in this lecture, we consider decision tasks where the decisions actually do not influence the state of nature. So you make a decision, but you do not actually act on it in the real world. If the decision should have some kind of important effect in the real world, then you may look at game theory or control theory that study these kind of things. Also, in this lecture and in this Bayesian framework, we consider only a single decision case, meaning that you have an observation and you make a decision, and that's it. There are also cases where you will have to make decisions sequentially, right? Maybe the observations will come to you one after another, different kinds of observations of the same object, and you will have to somehow update your belief about the state of the object in the sequence. So in a sense, this will be also studied in the hidden Markov models later in the semester. And a second remark, the hidden parameter k, the hidden state or sometimes class of the object, is here considered not observable, but it can be actually that the hidden state can be observed, but at very high cost, which means that, for example, in medical diagnostics, you will probably be forced to decide whether or not to apply some kind of very expensive, I would like to say measurement here, but the CT scan or magnetic resonance or something like that, that costs that are expensive simply. And if you don't feel that they are needed, because you can decide based on much cheaper measurements, then you will not, of course, say that you need these expensive tools. So the hidden state can be observed with much higher precision at a high cost, because in a CT scan or something like that, you would see the thing that you are looking for instead of estimating whether it is there or not, right? And the hidden state may be also a future state, which means that you estimate what will happen in the next step or next 10 steps. For example, you want to estimate the price of gold or other goods. And so it may turn out that the hidden state will be available to you later, but not now, right? So Both of these are actually sources for the training data that you will use in the machine learning part of this course. But if the hidden state wouldn't really be observable, then you will have no training data, right? No labeled training data. Okay. And yeah, another slide, another remark for this lecture. I use here the notation from the book of Schlesinger and Lavage, this 10 lectures on statistical and structured pattern recognition that denote the observations as X and hidden states as K and decisions as D and penalty function as W. But the same framework may be, of course, explained in other books using a different notation, right? So, for example, in this famous book from Duda, Hart, and Stork, they use these notations to denote the observation states, actions, decisions, and penalty functions. In yet another very famous book, Artificial Intelligence, Modern Approach, they use, again, somewhat different notation. So don't get confused that they use a different notation for the same things, right? The theory is the same. The notation for denoting individual entities is somewhat different, but it is still the same theory. Okay, and this is, yeah, maybe again a kind of side note. The decision tasks are very often studied in the pattern recognition field, and there are two types of pattern recognition, the statistical one and structural one. In statistical pattern recognition, the objects are represented as points in a vector space, which very often mean that, this means that each object is just a vector of numbers, or the observation at least. They don't have to be numbers in the sense of real values. They may be even, some discrete values, but it is a vector of discrete values, for example. In structural pattern recognition, the object description, the observation, contains some kind of structure which is represented and used for the recognition. So very often in that field, the objects are described using graphs or sentences in certain grammar, etc. Right? So this is somewhat more complex field, and sometimes it's transformed into a statistical pattern recognition by designing some features based on those structures, and and you make basically a vectorial representation out of the structural one. But of course there are some structural recognition methods that really use the structural description to make the decisions. This is just for completeness, so that you do not think that only the statistical pattern recognition that we deal with today here is the only field of pattern recognition. And now we get finally to the Bayesian decision theory. We basically have all of the blocks that we need, maybe with one exception, and that's the risk. How do you compute the expected penalty that you pay when you use certain strategy, certain decision strategy? And I have another question for you. we need to compute basically the expected value of the penalty when using certain strategy, right? You should probably know that the expected value of some discrete random variable w is computed like this if all the values of that variable are equally probable, or it is computed like this. So it's the probability of a value times the value. So it's a weighted sum of the values in the general case if they are not equally probable. And why I'm talking about this? Because that's basically my question. We have a set of observations X, the hidden states K, and the decisions D. We may have all the probability distributions that we need, so we have the complete statistical knowledge. That's fine. We have also the penalty function W, and we have one particular certain decision strategy Q. And we would like to compute the expected value of the penalty W for certain strategy Q. And my question is, which of these expressions is correct expression for computation of expected value of penalty W for a certain strategy Q? So give me your choices. Maybe you remember that from the cybernetics and artificial intelligence course, but it can be basically derived just by reasoning about what the individual things mean. So I give you a few moments to decide. Okay, so last few seconds. So thank you for your guesses or tips, choices. So it seems that B is the prevailing option, but not really winning by large margin. There are people that think that all the rest are maybe plausible or can be correct. So let's explain it a bit. Okay, so Q, this is the strategy that we consider, is the mapping from X, hidden states, to decisions, right? So this rules out probably this, because here the Q should accept K, hidden state, which is not the case. The decision strategy is mapping from the observation to decision. And this rules out also this possibility, right? From the same reason. QX, So the decision for observation X here, the strategy gives us certain decision, is put together with the hidden state into the penalty function, right? The penalty function is a mapping from hidden state and decision to some real number. So both of these things are actually, let's say, syntactically correct in the sense that the inputs, the meaning of the inputs is correct, right? So this W tells you the penalty that you pay in hidden state K for a decision D, which is QX, the output of the decision strategy. And you must weight it by the probability that the combination of observation and hidden state actually happens, of that particular observation and particular hidden state. And you must sum up across all the possible pairs of observations and hidden states. And that will give you basically the risk of the decision strategy Q. The last option D is not correct because here you basically sum up only across the hidden states, which means that the result that will be from here is again some kind of function of X, right? The X is not zoomed out of this expression, and maybe even of D here as I look here. So this doesn't make sense much, but B is the correct answer. So most of you was right. The majority of you was right. That's great. So thank you for your tips. And yeah, so let's move on. So this is just the definition of the Bayesian risk. The risk describes how good a strategy Q is, right? This is the function of Q and describes how good a strategy is, and it is the expected penalty you pay when you use strategy Q. And the strategy that minimizes this expected risk is called the Bayesian strategy, the one optimal Bayesian strategy. If you think about it, and if you perform some manipulations of this risk definition, it turns out that you can transfer the definition of risk to this expression here, where this R with two arguments are QX and X, or in other words, risk of decision when decision for observation X is defined like this. So this actually means that you can basically concentrate on each observation alone and choose the right decision for each observation independently of the other observations. And that's the most important result actually in Bayesian decision tasks, which means that you prevent the exponential explosion of the possibilities. You just choose the right decision for each possible observation and you evaluate the decisions using this partial risk. Okay? So it is the partial risk, it is expected penalty for decision D given the observation X, and you just fix the observation X and you Just go through all possible decisions, and based on this expression, you choose the one that has the lowest partial risk, and that becomes part of your final decision strategy. That's what this expression here says, that you can construct the whole optimal Bayesian decision strategy by minimizing the partial risks for each observation, choose the right decision. That's it. So any questions so far to this partial risk minimization or risk minimization in general? So I don't see any. That's great. Oh, maybe Domenico Dan píše zprávu. Thank you. You're welcome.
Yeah, I've seen this a few times, and it's been hard to follow the reasoning, but this was pretty easy, so thank you.
Great. And we will have actually an example for that in the lab session. I don't know whether we will get to it today or next week, but you will see a particular example there. Okay, let's move on. Yeah, here's some, again, additional slide with the remarks to Bayesian strategy characteristics. Just notes, right? So we deal just with finite x, finite k, and finite d, but of course the framework is more general in the sense that you can also derive a Bayesian strategy for infinite or continuous x, k, and d. You would have to replace the summation with integration, etc. But the framework is general enough to solve even this case. This is quite important thing. Bayesian strategy is deterministic. For example, my wife can come home and she finds that I am not at home. Okay? And she knows that with probability of 95% I am in pub, and with probability of 5% I am, I don't know, playing tennis or doing sports. Well, nowadays these probabilities would be completely different, but still. What should she do? What is the optimal strategy for her? Is it just go where is the maximum probability where I can be? Just go search for me in the pub? Or should she take some kind of randomized strategy that she should, you know, run a random number generator, and with 95% should she go to pub, and with 5% she should go to the sports center? This note tells you that she shouldn't take the randomized approach. She should behave deterministically because this is the optimal way. She should always go to the pub first to look after me. Okay? That's basically what this says. Don't use randomized strategies. The optimal ones are deterministic. Okay, and then there is this Bayesian strategy that divides the probability space to d convex cones. Wow. Yep. So this is a remark, somewhat more theoretical, but if you consider how this what is this probability space, and what is cone, and what is convex cone, etc., you will find that it makes sense. And it also builds some foundation, or at least some argument for using linear models for classification. We will see that in future lectures, because the Bayesian strategies are actually linear as well. They are convex cones which can be composed of linear functions. Okay, just enough for this remark. I can see that we have 15 minutes left. Okay, so I will have to maybe go a bit faster. I would just to point out two special cases of the Bayesian decision tasks. Very often you want the decisions to be the same as the set of hidden states, which means that you try to estimate the hidden state, right? That is very often the case in practice. The goal in this case is very often to minimize the probability of an error. You want to maximize the precision of your estimates, of course. And to minimize this, you can define the penalty function like this. So your penalty is 0 when your decision is correct, when your decision is the hidden state, the true one, and the penalty is 1 if you do not, if your estimate is not correct. And in this case, you can find the optimal strategy by minimizing this probability of incorrect decision, which in turn actually transfers into the maximizing this conditional posterior probability of state given the observation. So if you are able to construct this function, posterior distribution of hidden state given the observation, then you are able to solve this quite efficiently. So you basically decide for the most probable case for certain observation. And this is called the maximum a posteriori estimation. Sometimes you will see the abbreviation MAP, maximum a posteriori. And there is one generalization of this task. Basically, you do not have only two possible decisions, like two possible decisions. Two possible values of the penalty function W. You have three of them. And the set of decisions is not equal to the set of hidden state, but to the set of hidden states plus one more decision, which is I don't know. You basically refrain from deciding, right? I don't have enough data to decide sufficiently with sufficient what's the word? I'm not sure enough, simply, right? So if you define it like this, the penalty function is 0 if your decision is correct, is 1 if you decide to decide and your decision is incorrect, and you pay a very small penalty epsilon if you just say, oh, I don't know, I don't have enough data, I'm not sure. And in this case, the decision strategy may be constructed quite easily just based on this posterior probability of the hidden states. So basically you find the hidden state which has the largest posterior probability. But if this largest posterior probability is not high enough, here, then you issue the don't know decision. And if it is larger than some threshold, 1 minus epsilon, then you may afford to say, okay, I am sufficiently sure that the decision is correct. So this is some kind of extension of this task on the left-hand side with the don't know decision. Okay, what are the limitations of the Bayesian approach? Well, basically they all the source of the limitations is in the assumptions of the Bayesian approach. So we said that the Bayesian approach needs to know the penalty function W. It needs to know the prior probabilities of states, pk, and it needs to know the conditional probability of observations, px given k. And these two together give you the joint probability distribution of pxk, right? So, what happens if you don't know the penalty function? Maybe you don't know it. Maybe it doesn't make sense to create one because not all the errors that you can make during the decisions are somehow comparable. So, for example, if you have some judicial trial, like murderer and trial, right? Is he guilty or not? There are two errors that you can make. Either you convict an innocent, which is a huge harm for one innocent person, but the other error you can make is that you let the killer free, right? Which is maybe a potential harm for many innocent persons because the killer may kill again. And how do you measure which of these two errors is actually more important to you than the other? What's the penalty that you pay for one error and what's the penalty that you pay for the other? So sometimes it is very hard to apply the Bayesian approach because in that particular application the penalty function cannot be constructed reasonably. So the question, isn't that symmetric? Convicting an innocent person means letting the killer free. No. These are two completely different things, right? Either you are a killer, and then if you get into the prison, that's the correct thing. But if you are freed in the sense that found unguilty, then it is an error of the test, right, of the decision process. And if you are not a killer and you are found guilty, it is again an error of the decision process, but completely different. So they are symmetric in the sense that you can draw some kind of matrix and say, okay, these two things are fine and these two things are not fine. So in this sense, it is symmetric according this axis, but these two things here and here are completely different in the meaning, and it is hard to evaluate which of them is worse and which of them is better. Both are bad, right? But yeah, it's even hard to talk about it and to explain it, maybe. So I hope that you see that there are cases when the penalty function is not easy to be constructed. And then, of course, there are cases where you may not have the prior probabilities of states, maybe because the hidden states are not random variables, and thus the probability actually does not exist at all. Or they are just unknown because you don't have enough information. The same holds also for the conditional probabilities of observations given the hidden states. Yeah, basically they may be something which is non-random in that process, and then these conditional probabilities do not exist. Only some kind of these probabilities exist, and yeah, it's then more complex. But I don't want to spend much time on this. Simply, if you do not have everything that Bayesian framework requires, then you can't use the Bayesian framework, at least not properly. So we get to the non-Bayesian decision theory, and that's basically everything that is not Bayesian. So if you don't have the penalty function, or if you don't have the both of the parts of the joint probability distribution, you have to use something else than the Bayesian approach. And all the machine learning methods are basically non-Bayesian, right? All those that we will talk in the next few weeks are non-Bayesian. And here I want to just point out a few special types of non-Bayesian decision theory, where you don't have to learn from data, which can be somehow solved, at least to some extent, without learning, right? Okay, so non-Bayesian decision task, if you cannot use Bayesian, that's it. The strategies that these tasks actually result in are still of a similar type as the Bayesian strategies. So they divide the probability of space to a set of convex cones. And very often these non-Bayesian tasks, which I will talk about in a few minutes, can be solved by linear programming methods, numerically, in a sense. But of course, there are many other non-Bayesian decision tasks for which the solution is not known yet, or that requires machine learning to learn from historical data. So the first kind of non-Bayesian decision tasks for which we know how to solve it, at least to a certain extent, is this Nyman-Pearson task. And basically this is the task that you solve in statistics when you describe the statistical tests, right? There is the test that may come up, you have to, zero, or is it zero? Hypothesis, zero hypothesis, yeah, zero hypothesis. And you test whether the hypothesis can be true or whether you have sufficient data to say it can't be true, right? And this is very similar. Actually, it is the same thing. So you have observation X, and you have two states, 1 and 2, the normal one and dangerous one. That's the zero hypothesis and the alternative hypothesis, basically. Null hypothesis. Thank you. Thank you very much. That's the right term. Null hypothesis. Sometimes you really can't remember the right term. Thank you, Pavle. Great. So the hidden states are basically the hypothesis, the null hypothesis, and the alternative. So your task is, your decision task is, given the observation X, decide whether the conditions are normal or dangerous. Basically, whether you can or cannot reject the null hypothesis. And in this formulation, you don't need the prior probabilities of the hidden states of the null and alternative hypothesis, and you also do not need the penalty matrix or the penalty function. Because you can assign two numbers to each decision strategy. The probability of false positive result, false alarm. So that's basically you sum up all the probabilities across all observations for which you decide for an alternative hypothesis or for class 2, across all observations for which the strategy decides for the class 2, you sum up the probabilities that the observation actually comes from class 1. And that's the probability of false positive result. And the other way around, for all observations that really truly, the strategy decides that they should belong to class 1, you sum up the probabilities of generating them when they actually come from the second class. So you basically, the probabilities of the type 1 error and type 2 error, if I should say it in statistical terms. And then you may basically apply this Neyman-Pearson task formulation, which finds such a strategy that ensures that one of the errors, the omega 2, which is the overlooked danger or probability of false negative result, is not larger than some small epsilon. In statistics, you use 5% or something like that, or 1%. And you try minimizing the other error. Very often it is in such a way that if you have one error large and the other error small, then if you try to minimize the first one, then the other will go up, right? And here you have some limit on this small probability, and you try to push this error down as much as possible up to the point where this error, the smaller one, is the maximum allowable, and that is your optimal strategy. And you can basically decide on based on the likelihood ratio, which is just the probability of the observation coming from one class divided by the probability of the observation coming from the second class. And if this ratio is larger than some threshold, then you will decide for one class, and if it is smaller, you decide for the other class. So the decision strategy in a way is simple, but you have to understand the definition of the task.
And the theta is a function of epsilon, or?
Pardon me?
The theta here, that's a function of the epsilon, or how do we get the theta? Or
theta, yeah. That's basically what you will get from the linear program that you solve here.
oh, okay, thank you.
And yeah, And there is another formulation, maybe somewhat similar. It is called a minimax task. In this case, you have more than two hidden states, and you still want to estimate the hidden state based on the observation. And now each strategy can be described not by 2, but by k numbers, where the k is the size of the hidden state, the number of hidden states. So basically, it's the conditional probability of wrong decision under the condition that the true hidden state is k, right? And the computation is the same as in previous case, where only 2 classes were present, but here you basically say, okay, I have a class k, I have this probability of generating x when the true class is k, and I'll sum up this probability for all x's where my strategy gives me a incorrect decision. And that's the probability of incorrect decision in the hidden state k. And the minimax formulation is basically, minimax task formulation is basically to find such optimal strategy q star such that it minimizes the maximal error. So now you have basically more than 2 errors that you can make, and you find the maximal one, which is here, this one, and you try to push it down. You minimize this error, right? But if you push this error down, in general, the others will go up somehow. And once this error somewhere equals with the error of some other hidden state, then that's the minimax strategy, right? Because you cannot minimize the maximum more. Okay. So there are 2 slides as a side notes that there are, let's say, 2 other non-Bayesian tasks which are similar to but not exactly the same as the Nyman-Pearson or Minimax strategy. Their formulation is somehow different, but they still fall in the same class, and they can be solved in a similar way as the previous ones. The Wald task and the Linux tasks. I will not go into details here, sorry. And yeah, that's probably it. So today you saw how you should or you could approach the decision strategy design problem optimally in the Bayesian framework, which requires you to know the complete statistical information about the observations and the hidden states, so about the combinations of x and k. And it requires also the penalty function w, which assigns a penalty to each combination of decision and hidden state. So how much you pay if you decide D for hidden state K. And the Bayesian decision strategy is the one that minimizes this expected penalty, and the expectation is taken across the joint probability distribution of hidden states and observations. And if you cannot solve a decision task in this framework, then you have to resolve to something else. There are a few typical cases that can be solved in a principled way without the Bayesian framework, but usually you will basically apply some kind of machine learning. You will have to collect data which will serve as a substitute for the sufficient or not sufficient for the complete statistical information. But of course, this is imperfect because the training data is finite, etc. And we will learn about this in next weeks. Yep, so that's it. That's the end of today's lecture. So thank you for your attention, and I will stop the recording. And if you have any questions, you can ask right now.